Now that exam 1 is over with, we're going to move on to the next collection of material, the Unit 2 material. And one of the things that falls under this is a continuation of the stuff on correlation that we were talking about. And this brings us to the least squares regression. And the least squares regression is pretty much a direct extension of what we have done. It will now ultimately add a line that best fits our data. So we'll see that here momentarily. But to sort of talk you all through how this does extend from the previous section. So before we found how strongly two variables can be correlated. So we were talking about the correlation between two variables. So when you find a linear correlation, then you can draw a line if you have a scatter plot, or you can construct a line, and this line is going to give you the goal is for this line to give you a very good indication of how to predict values that may not be given to you. So an equation that lets you know, okay, well, if I have a value, an x value that appears in this spot, or a y value that appears in this spot, I have some degree of certainty as to where an observed value may lie. And that's kind of the goal here. We want to basically extend correlation to a formula. So that allows us to help predict other observed values that we may obtain, which we'll see here momentarily. The first thing we're going to talk about is this idea of residuals. So residuals is a difference between an observed value and a predicted value. So the observed value would be a specific data point that we found in a study. And the predicted value would be what we think that value would have been. And so normally we predict values based off of trends, patterns. If you see a trend going up, then you probably think that the point that will be on the far right will also go up in that trend. So that would be a prediction, and we might observe something that may fall in that general area or might not. And we can see so residual can be positive or negative because it is a difference. If the residual is positive, then the observed value is greater. And if it's negative, of course, conversely, the predicted value is going to be greater. So it's just a difference between the observed value and the response, or in the predicted value, and it's the y values in particular. These residuals, these differences between observed values and predicted values, well, these residuals lead to this concept called a least squares regression line. This line, so this is the namesake of the section, the least squares regression line is a line that is used to best fit a collection of data points. And again, this gives us a more concrete understanding of the trend of the data. And if we were to obtain a point somewhere, then we might have an idea of where that might go in relation to the other data points. So each point, so this is going to be, so the way you can visualize it, and we'll see this later, is you'll end up drawing a line through your scatter diagram. And each point on this line represents all of the predicted y values. So these are going to be the predicted y values. So these predictions will hopefully give us a good idea as to what other observed values may come out to be. It doesn't have to be perfect, but these lines just want to be approximate. this line will travel through the mean of X and the mean of Y as an ordered pair. That's another important data point, or another important point in general. The regression line always travels through the mean of the X variable and the mean of the Y variable. So we can always find the mean corresponding to quantitative variables. And so this line will at least always go through that mean. If the linear correlation, so remember, we talked about linear correlation before, we just typed that in the calculator. If the linear correlation was positive, or in other words, there was a positive association, the slope of the regression line is going to be positive. And similarly, negative and negative slope. So positive correlation is going to be a positive line, negative correlation, negative line. So additionally, so you might remember from maybe high school, or if you took college algebra, a line can always be represented as mx plus b in general. Instead of an m and a b, we're going to use an a and a b. Mainly this notation is used because the calculator gives us the answer as an a and a b. So we're going to use that notation I just highlighted. And notice the y has a little hat on top. So the hat distinguishes this version of y from the regular version of y. The regular version is the response variable, but y with a hat represents the regression line, which is different. And as I mentioned, the linear regression command in the calculator, which is exactly the command that we've used to find the correlation coefficient, we're going to use that throughout this section as well to find the regression line and the coefficient of determination. So let's go ahead and look at some of the examples here and get an idea of what this looks like. So I posted this data set before in the previous section on the acceptance rate. So out of all the applicants that apply to a school, how many of them are actually accepted? And then out of those accepted, how many of those actually graduate in 4 years? And the first thing we want to do is determine the least squares regression line. So this is going to be pretty much a quick tutorial on how to find this in the calculator. And you're going to find that this is the exact same process for finding the correlation coefficient. In fact, it's very much associated. So if we take our calculator, well, definitely you need to make sure, I just reset my calculator, so I need to go in and make sure diagnostics is on. As I mentioned in the previous section, if you already did this, then this should be fine. I need to make sure diagnostic is on. If that's on, then the next steps will work out the same way as mine will. But we need to go to stat and edit. And as we did before, we need to put in the X and Y values. Just need to make sure that L1 is where the explanatory variable goes. So that would be the 13, 24, and all of those values here. The acceptance rate here, just as a reminder, the acceptance rate is the explanatory. For your graduation rate is the response. And so let's keep going. 40, 48, I'll go ahead and type in the rest of these. with those, I can go ahead and type in the 4-year graduation rate as well. And so we're going to put this in the calculator the same way as if we were finding the linear correlation coefficients. Remember that we quit out of this, go to stat, and when we go over to CALC, there's linear regression. It's all under there. And when we do that, and provided you turned on diagnostics, you should see exactly this. And what this tells us, so the way we interpret all of this information, so basically they're telling us A and B. So if a line is represented as y hat is equal to ax plus b in general, then what they're doing is they're telling us A and they're telling us B individually. So that means all we have to do is write down y hat. The A, they tell us, is negative 0.52. I'll just round it to 2 decimal places. X plus, and then the B, they tell us to be 87 point, I'll call that 97. I'll round to 2 decimal places. So I used A and I used B. And this is the least squares regression line. And this line is a good fit for the, or the best fit rather, for the information in the, well, the data sets that we obtained. So the way we can interpret this, for every unit increase in, so remember the slope will give us an idea about the rate of change, just like as you've probably learned about in high school with mx plus b. So every unit increase in acceptance rate or in other words, the explanatory variable. So every unit increase in the x value, the y value is going to fall. The y value is the 4-year graduation rate. Or in other words, whatever the response variable is. That 4-year graduation rate falls by, well, that's what the slope tells us. Falls by already implies the negative, and then they just want the 0.52, the slope. So the magnitude of the slope. Because they already said falls by, which implies that falls by is the negative in words. So now we have a line, and now we have a little bit of interpretation, mainly of the slope of this regression line, which is A, which tells us about the rate of change. And from here, we can go ahead and graph the least squares regression line. Now, if you are given this on the homework, they will just make this a multiple choice thing. This was the scatter diagram we found in the last section. So we plotted all the points by hand for this problem. So I just gave the scatter plot here, and our goal is to add the particular line. So I'm going to write the line again, just so I can scroll up some more. Okay. So we're trying to ultimately graph that line, well, on this graph here, trying to plot the line on this graph. And some of the answer choices may not have the correct scattered diagram to even begin with, so those would be gone. So notice another indication that helps our favor is that the slope is negative, which by definition, the trend needs to be negative, which it is. So that's a good indication. Some multiple choice ones may have the scatter plots going in a positive direction, but the trend needs to go in the direction of the sign of the slope. If the slope's negative, the trend needs to go down. So if anything, this gives us a good intuition. And so the best way to graph this by hand, I feel as though in 105 and 151, there is a fairly similar method of doing this. This is finding intercepts. So, but really what we're going to do is I'm going to determine, well, not that point, because we don't know if that point's there, but I'm going to figure out where the point falls at on 100 and where the point falls at on what looks like 15. I'm going to figure out those 2 points, which basically means I would do 0 for the x-axis, but the graph doesn't go out that far. So I'm going to do when x is 15, which very simply means I'm going to plug in x into that formula we found. Oops. So x now becomes 15. And this is us trying to establish 2 points for which the regression line will go through. So this is going to be one of the points. So this is negative 0.52 times 15 plus 87.97. And it comes out to be 80.17. So whenever I plug in 15 for x, I get about 80.17, just a little bit above 80, something like that. It doesn't have to be perfect, but it just gives us an idea. So notice how I have a red point there now to distinguish that the red point is going to be different than the observed value. The red point is a predicted value because it deals with the regression line. So trying to bring this terminology into play here. And then the other value was x is equal to 100. So in other words, I'm trying to figure out the x values on the far left side and the far right side. And so it's the same exact thing for the 100. Negative 0.52 times 100 plus 87.97. And we get 35.97, another observed value. So whenever I plug in, so I did 15 just now. So with 100, whenever I plugged in 100, I got 35, which I'm guessing that's about 30. So I would say about right here. Again, doesn't have to be perfect. It's giving us another predicted value for which we can try to actually scale a line. And so just to make sure I could scale this line well, I'm going to use a little tool here. But basically, we're just connecting the dots here at this point. That's all we're doing. So the two red points that I have, just drawing a line connecting them. And this is the line that is the best fit for all the data points. So notice all the data points have pretty close proximity to this line. They're not on the line, and we never expect the points to actually fall on the line. However, we are just looking for a very close approximation of these points. And this trend ultimately allows us to predict other values that we may receive. So we may be able to predict, well, actually, we'll do a problem like that momentarily here. This is the regression line in a visualization as compared to a scatter diagram. And again, notice how the points are very close, and these points, their distance away from the line, that's called the residual for each point. So just to, again, bring some more terminology together. So does it make sense to interpret the y-intercept? Now the y-intercept, this is whenever x is equal to 0. That's the y-intercept. We see in our graph, though, that for when x is 0, we don't necessarily see that value on the graph, because the lowest x value we have seems to be, it's like 15. But that doesn't mean we can't interpret x is equal to 0. So let's look at when x is equal to 0, that means the acceptance rate is 0. So the way we're thinking about that is, should we consider a school that has an acceptance rate of 0%? And that does not make any sense. No. So the answer is no. Schools do not have an acceptance rate of 0%. Is the y-intercept. So that doesn't make any sense. There's no school that has an acceptance rate of 0. But something we can do, instead of looking at this y-intercept, or not looking at it rather, we can predict the graduation rate. So notice it says the word predict the graduation rate when the acceptance rate is 20%. So if we scroll up to our data set, there's no acceptance rate given that is 20%. None of these are 20. Some of them are kind of close, but what this regression line does, and ultimately the formula that we have obtained, will allow us to predict what may result whenever we supposedly postulate that an x value or a y value is a certain value. So the acceptance rate, remember that's the x. So our formula that we had was negative 0.52x, negative 0.52x, which now we can plug in 20, plus 87.97. So this formula that we have obtained helps us predict a graduation rate, given the acceptance rate is one of these values we desire. And so all we have to do is simply plug that into the calculator. So negative 0.52 times 20 plus 87.97. So what this tells us is that the predicted graduation rate, provided that the acceptance rate is 20%, is 77.57%. So again, this is not a value we observed, but this is a value we predict because we used the regression line to help us determine this. So it's a predicted value. We predict this is the case. We never observed this at all. We're just predicting it based off of our model. This is used a lot in business. This is used a lot in sciences. People take trends in data and then use that to predict perhaps future trends or previous trends, or maybe trends in the middle that you might have missed. Observe trends in the middle. So this idea of a regression line is very important. It's used in many different branches of not even just the sciences, but again, business, stocks, this is used all the time, and biology, about carrying capacities, logistic models that's kind of a similar idea, but this is very important stuff. Correlations are very important in various fields. And one more question we have at the bottom. The acceptance rate at a university outside the United States is 80%, and the graduation rate is 60%. Is this above or below the average graduation rate, whose acceptance rate is 80%? So what this problem is asking us is, if we consider a university outside of the United States, how is that going to fare with our predicted model? Will that be above our predicted model or below our predicted model? And that's what we get to find out here. So basically what they're telling us, so the rate outside the United States they're giving us an ordered pair. They're telling us that X is 80, because they say the acceptance rate is 80, and then they tell us that Y is 60. So far, there's nothing to plug in. They told us everything. And now they want us to compare this to the formula we found for universities in the United States. So in other words, what we are doing is we have our formula. This was the formula we found. The X value, we're going to plug that right into X and see, does their outputted value of 60, is that above or below our outputted value in our predicted model? Does it match? Or is it significantly larger, or is it significantly smaller? So we're plugging in 80. We're going to compare the final answer to that 60 that we had. And so we plug this in. We simply obtain negative 0.52 times 80 plus 87.97. So using the United States model, which was the model we had the whole time, in the United States, the graduation rate on average would be 46.37. But in this other country, their graduation rate would be 60. So is this above or below the average graduation rate? So ultimately, we are comparing the 60, 46.37. So this is above the average graduation rate. Because the 60 is greater than the predicted value. In other words, the observed value is larger than the predicted value, or above the predicted value. And this doesn't mean that our linear regression model is incorrect, that the line that we got was incorrect. Our line applied to universities in the United States. So when we looked at a university outside of the United States, it was expected that this data point would deviate from our best fit line. But these are various ways in which we can interpret the regression line. Does anyone have any questions about this before we move on? If not, let's go ahead and move on to something that is also very much connected and will be in the same series of steps that we use to find the linear correlation coefficient and the regression line. And this is called the coefficient of determination. The coefficient of determination, so the technical term of it, the proportion of total variation in the response variable that is explained by the least squares regression line, which sounds very technical. I'd rather look at it as, so it's denoted R squared. That's probably the most important part from that first paragraph. The best way I like to look at it, this is a measure that tells us how well the least squares regression line describes the relation. So basically, how good of an indication is that line in predicting future values or values that are not necessarily observed? That is the best explanation for the coefficient of determination. It's just a measure that tells us how good of a fit that line that we drew is, or that line that we found is, in terms of predicting values. And so this R squared is found in the calculator the same exact way that we found R, or A or B. So we're going to find that this is just a very slight extension from that idea. And we have some data values down here. The following data represents the number of days absent and the final grade in a Math 105 course. So people who missed 0 days on average got a score of 89.2, and missing 1 day, 86.4, and so on and so forth. And as you can see, as the number of absences increases, the final grade slowly decreases. And this correlation is pretty much true in any class. There is a strong correlation between classroom attendance and your final grade. And what we're going to do is first find the least squares regression line, just like we did before. Now this means you need to choose what the explanatory variable and the response variable is, which one would be the independent variable and which one would be dependent. I think that absences would explain, I think the absences would explain the final grade, or the final grade would respond to the explanatory variable, which tells us that in our calculator, when we go to type all of this stuff in, go ahead and clear out all of these, and we can start off. Really, we're putting these lists in order, ultimately. Clear out of those. And start putting in the absences first. And in the second list, we can put in the final grades. And if you're already ahead of me, you can go ahead and start figuring out the, do the same process you would for figuring out the linear correlation coefficient, pretty much the same steps we did just before. Okay. So again, what we did before, put out of that and went over to the linear regression command. Again, the same command we just did before for the regression line, we're doing that again. And if we all typed in everything correctly, you should get these values. So the least squares regression line, in general, I'll just write out it's AX plus B. But again, they told us A and B, so we can just go ahead and fill those in. A is negative 2.8, I'll round it up to 2 decimal places. X plus 88.73. Again, 2 decimal places. And that is the regression line. That is the regression line. That answers part A. This will be our best prediction of the trend of data given the previous data up here. So from here, part B says, predict the average grade of a student with 6 absences and compute the residual. So we're using this word compute the residual. We'll get to that in a second. But notice, just like in the previous problem, predict, normally when they say predict, that means we're plugging into that new line that we determined with 6 absences. So we'll start with that first. So our absences, we ask ourselves, are the absences the X values or the Y values? Absences are the X. That's the X. So they're telling us that X is equal to 6, the 6 absences. Negative 2.83 times 6 plus 88.73. So we're trying to predict the average grade of a student with 6 absences. 3 times 6 plus 88.73. So the expected grade is or predicted grade is a 71.75. So if anything, that is the predicted grade. But they also want the residual. Well, the residual is the observed value minus the predicted value. The observed value was what we actually found whenever we did the data set. Notice we already know what it looks like whenever we have 6 absences. It was up here. So whenever there were 6 absences, the observed value from our data was 64.3. So the residual is the observed minus the predicted, which is the 71.75. So 64.3 minus 71.75, and that is the residual. That is negative 7.45. So that is the residual. Now it's asking, is the grade of the student above or below the average? So the grade of the student, that would be observed. And the average, whenever they say the average, that generally refers to values from the line or from our regression line. So to answer the final part, so this would be below. since the observed value, or in other words, it's below since the residual is negative, or similarly, since the 64.3 observed value is smaller than the 71.75 predicted value. So they're asking, is the observed value above or below the predicted value? That's what that last sentence is asking. Now I went ahead, just like how MyMathLab will, generally for regression line stuff, they will give you a multiple choice option, and I'll do the same. I'll kind of simplify it here. So I already gave the scatter diagram, and we need to draw the least squares regression line. So we're drawing that. And so again, the regression line is, I'll just rewrite it here. And I want to draw the furthest x that I can find. See a 9 all the way over here. And it seems like this does go, in fact, to, I do think that goes to 0. Again, it doesn't have to be perfect. We just need some line on there. Generally, on your homework, this will be drawn well enough to where you can actually just determine which one is correct out of the other 3 incorrect ones. So if we plug in x is equal to 0, well, then that's negative 2.83 times 0 plus 88.73. Well, that's just simply 88.73. And that does end up being slightly smaller than this point up here. The point at the very top is the observed value at 0, which we saw was 89.2. We got 88.73, which is slightly below it. That's why I put the red dot right below it. And so we can also find when x is 9. Negative 2.83 times 9 plus 88.73. .3 times 9 plus 88.73. So 63.26 will give us the idea of where the other point is at. So that's 65. Probably predict that it would go about right here. Since the y-axis does stop kind of abruptly, a little bit below 65. And so all we have to do is connect those lines, or connect those points to make a line. And again, notice how the majority of the points seem to be very much centered around the line, but there is one outlier over here. There's that point that's really off to the side. And what they're wanting us to do is, in addition to drawing this line, they also want us to label the residual. Well, the residual is the point that I just called out. And the way they want us to label this, they want us to physically draw the distance from that outlier, which I'll circle in a little bit thicker here, from the corresponding point on the graph. That blue line is the residual. So not only did I draw the regression line, but I emphasized the distance from the outlier point to the line. But all the other points seem to follow very closely. So that would be the residual. So you'll see that on the homework. They'll have that sort of line, and you have to pick the one that best represents the residual. And this also makes sense. We can tell that the residual is below the line because we drew the line down, or equivalently, we just see that the outlier point is below the line. From here, we can really quickly find out the coefficient of determination, which tells us how good the line is. And if we bring up, so I'm going to go back to linear regression, the same command we did to find the regression line, you will see r squared in the calculator. And whether it's capital or lowercase, it doesn't matter. The point is r squared, they tell us, is 0.89. I'll do 4 decimal places, just like that. So that one should be really easy to find. The calculator tells you the coefficient of determination, which we can immediately interpret. Again, if you don't have diagnostics on your calculator, you're not going to see r squared and r. So that's why you turned on diagnostics. But to interpret this, that means that the least squared regression line explains, and this is when we use the coefficient of determination, 89.76% of the variation. What is it the variation in? It's always whatever the response variable is. Total variation in the response variable. So whatever the response variable is. And in this case, the response variable is the final grade, the y value. So really, we're going to look at now, basically what F and G are asking is, well, is the coefficient of determination resistant or not? That's basically what it's asking here. A student with 10 absences is then included, and their final grade is a 35%. How does this addition affect r squared? So basically, if we throw in a new data point, so there's a new data point that we're going to add to our graph or our data set. A new data point. It's the ordered pair 10, 35. So I'm going to pull up the calculator, go back to our list. So before it only stopped at 9, I'm going to throw in the new one. So for 10, we have a new grade of 35. So we have a new grade of 35. So we can quit out of that and try to figure out the new correlation coefficient with the new data point. Now r squared, so the new r squared is equal to 0.7715. So how does this addition affect r squared? The new addition obviously decreases r squared. And again, it doesn't matter. Capital R, lowercase r, it's the same thing. The new addition decreases r squared. As we can see, r squared was originally 0.8976, and then it came out to be 0.7715. It's a drastic decrease. So is the point corresponding to this new student influential? Is it an outlier? I would like to say it is an outlier. So ultimately, is it an outlier? So is an outlier. So this is corresponding to the new point. So it is an outlier because its addition drastically decreased r squared, because r squared is a measure of how good the regression line is. If r squared, though, decreases, that means that line is less helpful to us in terms of predicting values. So this outlier truly is detrimental, because as soon as it's included, we just lost over 10% of certainty from going from 89-ish% to 77%. We lost over 10% of certainty in our line by the addition of one new point. And so we can probably conclude from that, that the coefficient of determination is not resistant. It's not resistant. So as we can see, one simple data point makes us lose a lot of certainty. One simple outlier can do that, which by definition means that the coefficient of determination is not a resistant measure. So does anyone have any questions about this before we move on to the next section? If not, then the homework for this section is updated in my math lab. Tentatively, I have it set for Friday. So please be aware of that due date. Probability rules, I'm not too sure yet. It depends on how much of the section we go through. But let's go ahead and start with the next, well, really the next chapter on probability, and in particular, probability rules. So we've been talking about really gathering information and interpreting it. And we've been dancing around this idea of interpreting percentages, which really help us with predicting various trends. Another way we can predict trends is by considering the probability that an event may occur. Now, if you took Math 105, you're probably familiar with some of this. And for the scope of this class, we are not going to discuss probability in as much of a detail as was, discussed in 105. But we're going to give it a little bit of a conceptual look. So this will probably be the best way to look at probability from the scope of this class, just thinking about it conceptually. So in this class, we're going to represent any proportion. So in 105, we generally represented proportions as fractions, as simplified fractions. And in this class, we're going to represent them as proportions. So basically, you plug the fraction in the calculator and see the decimal that pops out. So this is different than the percentage, because this proportion, as I put an example here, instead of saying there's a 10% chance of rain tomorrow, our answers are going to be generally formatted as there is a 0.1 chance of rain tomorrow. the proportion of 0.1. And this is because proportions are very helpful in mathematical computations. We generally do not use percentages, and instead we generally convert percentages to decimals and then throw the decimal version into the calculator or whatever other formula we're using. So same idea here. So we're going to deal with proportions. And this immediately leads up to the definition of probability. So probability is the measure of likelihood. That's pretty much it. It's how likely something's going to happen, the predicted likelihood that something's going to happen. So probability is a word that's used fairly intuitively. So again, the weather, that's normally a very common thing. We see it about COVID rates recently. There's a this percent chance of someone in this age group dying from it. It doesn't mean that these results have perfect predictions. They don't necessarily represent that. So, for example, if so I suppose the point I'm trying to make is best exemplified in example 1. So let me just wait to explain it there. But dancing around the idea I was about to say, in the short term, probability only determines an approximate expectation. And this can be shown in example 1 here. So the most common example we can think of probability is flipping a coin. You flip a coin, it's either heads or tails, provided this is a perfectly fairly weighted coin. So you flip the coin, and I think we all know that there's a 50-50 chance of getting either heads or tails. Now, it's not expected, if you flip a coin 10 times, it's generally not expected that 5 of those times are going to be heads. Even though you would think, well, doesn't 50% mean that you would get 5 heads if you flip it 10 times? In the short term, no. It does not mean that in the short term. In the long term, though, we will notice that the frequency of this occurring will, I guess the technical word is converge, but in other words, the frequency of this occurring will more likely approach the proportion, as best shown by this graph. So this graph down here from the textbook, the number of times you flip and the proportion of times you get heads. So maybe the first time you flip the coin, you get a tails. And then whenever you get a heads for the second flip, the reason why it's right here is because it's the proportion of heads. If you flip the coin twice and you get heads once, that's 50%. And so notice after, say, about 10 flips, you are not near the 50% range. You are not near 50% because in the short term, that's not what proportion tells you. But notice as you flip the coin more, the proportion of heads that you get gets closer and closer to 50%. And this is a very important idea. So this tells us about what happens in the long term. In the long term, if you were to repeat this experiment a bunch of times, generally speaking, your proportions will approach the stated probability. So in other words, short-term probability is only an approximation. Long-term probability or long-term experimentation or trials will converge or get really, really close to that proportion. And this idea is known as the law of large numbers. So this example, there's not really anything we're doing. This is just more conceptual based. But the law of large numbers, as the number of repetitions increases, the proportion gets closer to the probability. So that's ultimately what this is referring to. So this is all, again, all conceptual based so far. And this all has an interpretation that's going to be exhibited in the following examples. So this is all leading up to something. Well, first, an experiment is any process with uncertain results that can be repeated. So experiments are done all the time. But so it's basically any study. Go out and experiment the number of times you, say, flip a heads, if you flip a coin, or the number of times you draw a red card from a deck of fairly shuffled playing cards. Experiments are, again, that's another fairly intuitive word for anything, the process of anything you want to study. And this falls under, this could fall under statistical studies as well. And we have a few more words to define. There's a sample space and an event, which this is probably the most important terminology we've come across so far. So again, if you took 105 last semester, these words should seem very familiar. If not, put very simply, the sample space is the collection of all possible outcomes. So generally, the easiest example I could think of are if you take a bag of M&Ms and you pour them out into a bowl, all the possible outcomes, or the sample space, would be all the different colors of the M&Ms. I believe the colors, I wrote them down here. Yeah, brown, yellow, red, blue, orange, green. All of those colors would be that would be part of the sample space. The sample space collects all of the possible options. And an event is any one or any combination of the outcomes from the sample space. So an event can be drawing a brown M&M, or just grabbing one at random, or it could be grabbing a blue one, or it could be grabbing a brown or a blue one. Any collection of these events. And generally, an event is denoted as capital E, just for event. So the sample space is all the options. An event is just, generally in this class, we'll look at just one event. We don't really pound down too much in this class. An event is considered impossible if the probability is 0. Makes sense. If the probability is 0, then that means there's a 0% chance of it happening, in theory. An event is unusual if it's less than a proportion, if the proportion or the probability is less than 0.05, which translated means if there's less than a 5% chance of the event occurring, it's considered unusual for it to occur. An event is certain, the probability is 1. The probability is 1, that means there's a 100% chance of the event occurring. So that's some of the important terminology that I will be going through, mainly sample space and event. So we use the notation capital P with parentheses and a capital E inside of it to mean the probability that event E occurs. So now we're figuring out the probability or the likelihood of some particular event occurring. And there are some rules with probabilities. Again, if you took 151, this should all look fairly familiar. If not, any probability that we deal with in general must be in between 0 and 1. So all probabilities lie in between 0 and 1 when we look at them as proportions. This makes sense because any percentages that we look at lie between 0% and 100%. So it's the same idea. It's just we look at probability in decimal form, not percent form. And additionally, the sum of all the probabilities must equal 1. That's what this weird notation represents. The sum of all the probabilities of all the outcomes has to equal 1, which makes sense because for each event, there has to be a probability of that occurring, and for all the various events put together, there has to be a 100% chance that one of those events has to occur. So that's why the proportion is equal to 1 here. Now I referenced the bag of M&Ms. So let's say a bag of M&Ms was opened, poured into a bowl, and the probabilities of each color were determined. So basically, they were seeing the frequency, the relative frequency of each one of these colors to predict the probability. And so what they first ask is the table a probability model? So what that means is, does this table follow the rules of probability? Are all the values within 0 and 1 inclusive? They all seem to be within 0 and 1. So if anything, it passes the first one that I just checked at the top of the screen here. All of the probabilities are in between 0 and 1. There's no negative ones, and there's no probabilities greater than 1. So if anything, they're recorded just fine. But now the question is, do all the probabilities add up to be 1? 0.20 plus 0.18 plus 0.03. So basically just adding all of them up. Plus 0.18 plus 0.20. So if this comes out to be 1, this is in fact a probability model. So 0.2 plus 0.18 plus 0.03 plus 0.21, 0.18, 0.2. And we get 1. So this is a probability model. Because it follows all of the rules of probability. And then finally, wood color M&M is an unusual event. Remember, we defined an unusual event as any event less than 0.05. Well, that seems to be very clearly red. That's less than 0.05. Red, since 0.03 is less than 0.05. Simple as that. That's it. So hopefully that's pretty straightforward so far. So there's also the empirical approach for really approximating probabilities. Again, I'm going to keep saying this a bunch of times. If you took 105, this is the same formula we used before. It's the frequency of the occurrence divided by the total number of occurrences. So the probability is approximated by the frequency of the event divided by the number of total outcomes. So this is a generally intuitive idea. So if we look at a Math 241 class with 24 students and 15 of you all are freshmen, what's the probability that a randomly selected Math 241 student is a freshman? Well, there's the probability for that event is equal to the 15 freshmen, because that's the event, divided by the 24 total students. That fraction will give us a proportion. (15 divided by 24), 0.625. So that's the proportion. And one of the reasons why proportions are helpful is because of, say, part B. If 1,000 Math 241 students were sampled, what would we generally, how many of those students would we expect to be freshmen? So it would be, so the first part, in my math lab, it'll put about or exactly, but probability never determines anything exactly in the short term. So generally you want to use about instead of exactly. But if there's 1,000 students and you approximated the proportion to be 0.625, then this multiplication is going to tell you exactly how many students you would expect to be freshmen. About 625. If there were 100 students, it would be 62.5, which you would just simply round up to 63. So that's the empirical approach. So let's go ahead and finish up with the last problem here. We'll be done with, and this, after example 4, this is it for probability. We don't really focus on probability too much in this class. This is the furthest extent we discuss probability. So example 4, there are 36 combinations from rolling 2 fair die, and the outcomes for the sum of the 2 dice, you can have 1 and 1 to give you 2, or if you roll a 2 and then roll a 1, you can get 3, or rolling a 1 and a 2. So the sums go up from 2 to 12, ultimately, where the last one is if you roll a 6 and another 6. Now, when they say determine the sample space, remember, that's all of the outcomes. That's all of the different outcomes of these sums. So here, we generally use, so if you haven't taken 105, this is the main reason why we don't talk about probability too much. There's something called a set, and they use this curly braces notation. If you haven't taken 105, they use this curly brace notation, and they just list out all of the different occurrences. So basically, it's a list encapsulated by some curly braces. The probability of rolling a sum of 6. So the probability of rolling a sum of 6, well, it's not as simple as just saying that, well, so don't write this part down. Rolling a sum of 6, you might think, all right, well, there's 1, 2, 3, all the way up to 1, 2, 3, all the way up to 11 options. So you might think, all right, 6 is one of the 11. So then the probability would be 1 over 11. That is not correct, because there's more than one way of rolling a 6. You can get a 6 by rolling, you can roll a 5 and then a 1, or you can roll a 4 and a 2. And I'm out of time, so I'm just going to leave it here. I'll finish this last little part next time, but mainly focus on the second correlation homework in my math lab, the least squares regression. That is tentatively due Friday, and I'll figure out when probability rules is due, probably I'll probably make probability rules due next Monday or next Tuesday. Aside from that, that's all I have. Have a good day.